Hi, my name is Daniel, and today we'll be talking about the SEM that is being used here at the University of Florida. Hi, thank you for tuning in. My name is Daniel, and today we're going to go over what a SEM is and the application that we use it for here at the FICS lab.
So you might be wondering what a SEM is. An SEM is a scanning electron microscope that has a wide range of magnification and focus when compared to your typical optical microscope. It helps us gather topography, morphology, and optical and electronic properties. Over here on our right, we can see an electron gun that produces electrons that go through quite a few lenses, and it is focused down onto our sample. These electrons are then bounced off our sample, which become backscattering electrons, or their energy transfers to the electrons on the sample and produce secondary electrons, and these are picked up by our detectors. We also have an X-ray detector that's able to pick up on the X-rays that are produced from our sample. Now we use this so we can detect Trojans specifically here at our FICS lab, and we can also figure out whether or not there's any defects with our chips. Here we have an actual picture of the chamber of our SEM on campus. You have our sample down here, and then you have our beam gun up here. To our right, we have just pretty much a picture of what we see. So we have an incident electron, which is from the beam gun that hits the chip and produces a secondary electron or turns into a backscattered electron. And as you can tell, there's absorbed electrons and transmitted electrons that go through it. But specifically, we focus on the backscattered electron and the secondary electron. So just to talk about like the specific SEM that we use the TestCan Farah 3. This has three special instruments on it. You have the energy dispersive spectroscopy that measures all the energies of X-ray photons. You have the wavelength dispersive spectroscopy that measures the intensity versus X-ray wavelength, and then you have the cathode luminescence, which is an optical emission spectrometer. There's actually different types of electron sources that are used in SEMs. Specifically, this one uses Schottky. It's just because of the factors such as cost and brightness, and even probe current. So here you have a view of the SEM software. Fortunately, I wasn't able to go on campus and get into the lab and show you, but here's a screenshot of it. You have your presets right here. So your beam energy, you have your rotation, speed, magnification. You can change what the sample is here on this carousel or your stage. You can push it all the way up or close or away from your electron beam, which is right here. You also have your vacuum. You want to make sure that's on, and then you turn on this beam on right here, and then you have over here you have some more information such as depth of focus, your magnification here, and even your resolution. The example that we're going to go over is the Intel's 14 nanometer technology, the previous generation being this 22 nanometer technology. And as you can tell, there's been changes with fin pitch and gate pitch and interconnect pitch. And overall, it's a little bit harder to get a clear image. And that's what we're going to be trying to focus on today. So here we have a picture of the 14 nanometer chip. This is just the surface here. As you can tell, we have the voltage set here at 30 kilovolts right here, and same over here, but the view of field changes and the magnification changes. Now with the SEM, we're able to go through certain layers in our sample. Here we have three images, and all three images have very similar parameters. However, on the left side, we have an image
after 14 minutes of delayering. On the right side, we have two images that vary in kilovolts. So 1 kilovolt image and another one was a high kilovolt image, and these images are produced after 5 minutes. Again, here are some more images of our 14 nanometer technology. In this image on the left, you can see that we have a wide view field and a small magnification, and then to our right we increase our magnification and decrease our view field. Now these images are not the clearest, but we're trying to get clearer. That pretty much wraps it up. Thank you again for watching, and please take care. Bye.